Sustainability. That's a word we hear often today. We're used to living in the present, the here and now. But sustainability is about anticipating the future, learning how to meet our needs without compromising the needs of generations to come. People around the world are taking small steps that change how we live and work, conserving water, reducing our carbon emissions. Overall, we're simply beginning to see that reduce, reuse, and recycle are the foundation of environmental sustainability.
Natural ecosystems don't produce waste. There's no such thing as waste in a natural ecosystem if you think about it. Everything is cycled and utilized and captured again. Natural forests on the landscape produce clean water, and they produce fresh air. And so there are no wastes accumulating or otherwise generated. So those ecological systems are doing something right. And I think, in terms of sustainability, one aspect of sustainability in human economics and cultures is to, as much as possible, close those circuits and recycle and capture material and produce as little waste, what we call waste, which is a human concept, not a natural concept, as possible.
Some of the best sustainable environmental practices are not complicated. They're just practical, simple ways to reduce our human impact on the natural world. As our communities strive to become more environmentally sustainable, we aim to emulate nature in the way we manage our waste. For example, large-scale municipal composting diverts tons of nutrient-rich material from our landfills. Another important way of diverting waste is the reuse of a different source of organic, nutrient-rich material, municipal biosolids. Biosolids reuse offers us some amazing benefits. However, the process is not without its challenges. Over the next few minutes, we will explore the value of reusing this remarkable resource and the steps we are taking to meet these challenges. Let's begin at a wastewater treatment plant, where biosolids are captured and processing begins. Wastewater has two main components, water and solids. Treatment facilities are designed to settle out the solids, which after processing become reusable biosolids, and to treat water in the liquid stream, making it safe for discharge back into the environment.
Primary sedimentation follows preliminary treatment. In the primary sedimentation tank, we capture approximately 60% of the suspended solids present in the wastewater flowing into the plant. We do this quite naturally. We provide enough detention time within the tank to allow gravity to do the work for us. Solids settle to the bottom of the clarifier. Those solids, the raw sludges, are removed and pumped for further processing and treatment in anaerobic digesters. The next step in the treatment of the liquid stream in a wastewater treatment plant is biological. It involves converting dissolved organic material to a suspended solid mass. We do this biologically. As occurs in nature, bacteria basically do the work for us. Suspended solids that are converted from dissolved solids in this aeration basin flow into a final settling tank. In the final settling tank, we're able to settle out the suspended mass of activated sludge and send that material off to anaerobic digestion for additional treatment. The final step in the treatment of the liquid stream in a wastewater treatment plant involves disinfection. Disinfection kills pathogenic disease-causing bacteria. The final effluent, treated and meeting all ministry standards, is able to be safely discharged to the receiving body of water.
Solids which have been processed in digesters like these can be treated using a variety of technologies. In some plants, they are processed using alkaline stabilization. Some facilities can make pellets. Some produce liquid biosolids, while others produce a drier material. Regardless of the process, the finished biosolids are a nutrient-rich material, similar to the rich black muck found at the bottom of a wetland.
Nutrients from the byproducts of the sewage that we produce and the other activity that washes down the sewers and the drains and is captured in the residue of the sewage treatment system, which is the biosolids. And that represents, a rich capture of nutrients. If they were discharged in the environment, they would cause a problem. But if we collect them, and if we can close the cycle somewhat, if we can bring those nutrients back to the land, to the food cycle, and let them enrich the earth, we're closing the cycle. And that's very ecological, very sustainable model.
The wastewater industry is faced with two major challenges with respect to biosolids. The first is the volume of material. It is estimated that each household in Ontario produces approximately 1.2 cubic meters of biosolids annually, a volume that will only increase as population continues to rise. The second is one of quality. Not everything that ends up in a sewage treatment plant is organic or natural. The potential for contaminants finding their way into biosolids is a valid concern.
Here at the Ministry, we're committed to continually reviewing and updating our land application standards to ensure that they reflect new and current scientific research, which includes our emerging contaminants.
People often comment on the contribution industry makes to municipal wastewater, but it should be noted that industrial and commercial facilities upstream of the wastewater treatment plant must carefully adhere to very strict sewer use bylaws. Consider the products that you have in your own household that may get flushed down a drain and make their way to a sewage treatment plant.
Lotions and soaps, hairsprays, deodorants, as well as in a lot of cleaning products we use in our homes and at work.
Whatever gets flushed down the toilet, poured down a drain, ultimately ends up at the wastewater treatment plant.
There's lots of different things that can happen to these chemicals when they actually enter into a wastewater treatment plant. They can end up in the liquid stream and potentially be let out in sewage effluent. They can completely be broken down or mixed with other chemicals and become a new chemical or be destroyed. Or they could end up in that solid stream into the sewage sludge and eventually into our processed biosolids.
Wastewater plant operators licensed by the Province of Ontario regularly collect samples from all phases of the wastewater treatment process. Samples are analyzed in in-house laboratories and also sent out to accredited regional laboratories to determine and help the operator assess whether or not the treatment plant is operating effectively and to ensure that the treatment plant is meeting all of the criteria regulated by the province. Each and every one of us is able to help protect the environment and public health by refusing to use the sink, drain, or a toilet as a means of disposal for hazardous or toxic materials.
Managing biosolids is not just a local challenge, but one that is shared by communities around the world. Application to land is carried out globally, and scientists, agronomists, and human health experts are constantly studying and monitoring the process. Here in Ontario, there has been a great deal of scientific research and government focus on increasing our understanding of biosolids and of any potential impacts that may be related to contaminants within them.
Well, over the years in biosolids research, what we've looked at are specific constituents within the biosolids, whether it be heavy metals or nutrients like phosphorus or nitrogen, or some of the pharmaceuticals and personal care products, those types of things. But the question was asked, is this practice sustainable? Is it going to impact the soil that we're growing crops in? Is it going to impact the crops at the end of the day?
We took 4 different kinds of plants: corn, soybean, the common green bean, and Brassica rapa, which is field cover. And we took a look at various morphological developmental endpoints, when biosolids were land applied to them, and when in fact they were just grown in reference soil. But of course this was not enough. What we had to also represent was kingdom Animalia as well. And we did this then by taking a look at a major macroinvertebrate, springtails, and of course the common earthworm. If your municipal biosolids stress out these 2 organisms, what ends up happening is that you lose all of the fertility in your soil. So their environmental relevance is so extraordinarily important. What we found with all 4 plants, in fact, was that there were no morphological differences in anywhere along their life cycle development compared to reference plants. In fact, often the yield was significantly higher in the crops grown in biosolids. With regards to the springtails, while it was tremendously onerous to count all of their offspring, we found that there was no statistically significant difference between those who were in biosolids and those in reference soil. And with regards to avoidance behavior, no, there were no significant differences. This was also true then for the earthworms.
My research program is focused entirely on inorganic contaminants that enter soils as a result of agricultural practices, as a result of mining practices, generally as a result of man's activities. The most important pieces that we're interested in my lab is how those contaminants move from the soil into vegetation, and then how they move from vegetation into human diets, either by being fed to animals as part of the food chain or being directly ingested by humans as part of their diet. One of the sources of inorganic contaminants, such as metals, to soils is the application of fertilizers and biosolids to land as part of agricultural practice. One of the really important things to remember about these metals is that a large number of them are essential for human health. So without those in your diet, you will die. You need many of those elements, but there are a number of them, of course, that you don't need. Lead being one of them, arsenic being another. And those elements can be present in biosolids at very low concentrations. An interesting scientific challenge is, how do you predict where they're going to go? Are they going to become available and be taken up by plants? Are they going to become available and washed out in leachate? Or are they going to stay adhering to soil particles for a long, long time? And that really is the focus of my research. And biosolids and soils have a great capacity to bind these elements and make them unavailable for transport and for uptake. We're doing more mathematical simulations than actual measurements, largely because the previous work we did on actually measuring the increase in trace elements in soils as a result of biosolid applications, we can't find any increase. The increase is so small that we can't separate that out from the variability in the soils that exist before you put the biosolids on.
We looked at different methods of applying sewage biosolids to Ontario fields, and then tried to follow what happens to any contaminants that we might find in the biosolids. And what we found is that we are able to detect pharmaceuticals in the nanogram per liter range, or parts per trillion. I know that doesn't provide a lot of context, but in general what we think of when we hear about 1 ppt or 1 part per trillion, that equals 1 drop in 20 Olympic-sized swimming pools. So if you can try to think of, you have 20 Olympic-sized swimming pools in front of you and you put 1 drop in, that would be equal to 1 part per trillion, or 1 nanogram per liter.
When biosolids are applied to agricultural land, there is a rigorous process that must be followed. The regulations that must be met are designed to protect both human and environmental health.
The ministry has been approving the land application of biosolids to farmland for over 30 years, and we've had no objective evidence of impacts when best management practices as well as our regulations are strictly adhered to.
Environmental officers at the Ontario Ministry of the Environment conduct proactive inspections of land application activities to ensure compliance with regulated standards.
And with that as a history, the MOE and OMAFRA created a regulatory framework which uses that historical application to create a very stringent set of rules that are standardized across the province of Ontario.
This truck is being loaded with liquid biosolids, which will be applied to an approved local farm field at the farmer's request. The material has been sampled for testing, and the field has been prepared well before the delivery. Flags identify where biosolids can be applied without risking infiltration into water sources. The soil type and crop type have been approved for this application. On this land, there are no steep slopes that might cause the material to run off, another criteria for approved application. Incorporating the material into the soil reduces the impact of odors and keeps the nutrients where they are needed, in the earth.
This wheat field had biosolids put on 3 years ago in May, so we put it on and then we planted a crop of corn. And then we planted beans, and then that went into wheat, so this is the wheat field following those 2 crops. We used to have a hard time matching the county averages for our yields, but don't have any problem with that anymore. 6 years ago we started putting biosolids on our fields, and as far as the confidence in terms of how the quality control and everything like that, personally I have no concern at all, because with every industry there's guards at the door. There are people that are watching it. Doesn't matter if you're buying cars as far as safety or your own food that you eat. site, there's safety. Every industry, there's safety. And there's certainly a legion of people watching this program, making sure that, that the product meets the criteria.
Biosolids are sampled and analyzed by wastewater treatment plant staff to ensure that the biosolids meet provincial standards of quality as prescribed under the regulations of the Nutrient Management Act. If biosolids qualities are not met, biosolids are not applied on agricultural land.
While there are challenges to meet, the benefits of biosolids reuse are simply extraordinary. Beyond their reuse on agricultural land, biosolids have an incredible range of other uses and benefits. For example, commercial nurseries and larger reforestation projects benefit from the way biosolids amend soil by improving both the organic content and the ability of soil to retain moisture. Biosolids have helped restore vitality to soils in extreme conditions, such as on the site of strip mines, where the soil was previously unable to support any form of life. They can even be used as a renewable energy source, providing power to our industries and homes. Above all, biosolids are an amazing source of non-renewable nutrients which should be conserved, and a valuable resource that should be reused in a beneficial way. Treating biosolids not as waste but as a resource is just one simple but important step towards developing sustainable communities.
The focus of our regulatory framework for non-agricultural source materials like sewage biosolids is to provide better protection of human health, crops, and the environment.
And we've had no objective evidence of impacts when best management practices as well as our regulations are strictly adhered to.
You know, we have choices to make in a variety of areas. In the area of biosolids, it's about capturing not only actually the nutrient value that's in it, but also there's organic value.
It's a very sustainable product, too valuable to waste.
It works really well, and I'm really pleased, and it's done a really nice job.
We are all responsible for biosolids and for ensuring our choices do not compromise the quality of life of future generations. Choose a better and more sustainable approach to managing this valuable resource.